PhD thesis defense of Ji. Ji actually joined me in 2020, right? 2019. Yeah, so it's very interesting because Ji is one of the rare students that I have that actually was recommended by someone I know. So I was actually talking to Qiyue, who was still at Michigan State at the time, and she was telling me like, oh, I have this wonderful summer student who already finished very interesting work on using DFT for batteries, and he's writing a paper, and he's applying to UCSD. So I always like these kind of students because they usually, when someone tells me they are good, they usually have to put their reputation on the line. And I'm pleased to say that actually Qiyue was definitely correct. Okay? So Ji in the past 4 years or so have done very, very interesting work on developing machine learning potentials and using them to study lithium-ion batteries. So he has done both fundamental work on machine learning potentials as well as its application. So this is what you are going to hear about today. So with that, yeah, please go ahead.
Thank you, Shuping, for the very nice introduction of me. And hello, everyone. Welcome to my defense. As introduced by Professor Ong, I'm a fifth-year PhD student in Material Science and Engineering program. And today, I'd like to present my defense titled Insights into Solid Electrolytes from Long-Time and Large-Size Scale Simulations with Machine Learning Interatomic Potentials. So here is the overview of my presentation today. I will start with introduction of ab initio simulations of solid electrolyte and also what is machine learning interatomic potentials. Then I will dive into two major studies where we use machine learning interatomic potentials to gain better understanding of solid electrolytes. To be specific, the room temperature ionic conductivity issue and also the local chemistry and diffusion at green boundaries. After that, we will discuss about our invented method called direct sampling to do robust training of machine learning interatomic potentials. Following that, we will give you a summary and outlook for this defense, and I will end this defense with acknowledgement. So as we know, lithium-ion battery is the energy storage device that provides electricity for our electrical vehicles. However, it also has some safety issue, mainly because of the flammable nature of its liquid electrolytes. So by replacing those flammable liquid organic electrolytes with solid material, the all-solid-state battery hold the promise of giving a higher safety and also better battery performance. For those solid electrolyte materials, it has several requirements. To begin with, it needs to be synthesizable, and it also needs to be electronic insulating to prevent short circuit between electrodes. And it needs to have high ionic conductivity to do fast transport of mobile ion between electrodes. And it also needs to be compatible with electrode so that there's no degradation happening during cycling. So according to this diagram, we can see the pros and cons of different known solid electrolyte materials. And what we can see from this plot is that no single material actually fulfill all the requirements. That's why it's important for us to better understand solid electrolyte material and to give better design so that we can enable solid state batteries. And as computational material scientists, we study the behavior of materials with ab initio simulations, where the properties like total energy of a system is derived by solving the Schrödinger equation. So the exact solution of this many-body Schrödinger equation is intractable with a system of more than a few electrons. While with density functional theory, we can take use of the quantum equation, which is a much simplified way to derive the total energy of system by dealing with the charge density. And in this quantum equation, the only unknown term is actually the last term, which defines the exchange correlation energy of electrons. And we have to use approximations to approximate this term. And we have different approximations like listed out in this Jacob's ladder of density functional methods. And you can see that this plot shows the trade-off between computational cost and accuracy. So the higher accuracy we got, the larger computational cost we have. And most of those density functional methods or different functionals are implemented in the DFT software, which is very famous, called Vienna ab initio simulation package, that is ready to use for computational material scientists to study different systems. And specifically for solid electrolyte materials, from the result of density functional theory calculation, we can construct the phase diagram to study the thermodynamic stability of solid electrolytes. And we can also construct a ground potential phase diagram to analyze the electrochemical stable window for those electrolyte material. And we can also calculate reaction energy for electrolyte material versus different electrodes for us to come up with a good combination of materials for whole cell. And we can also study bulk modulus and shear modulus, which are important mechanical properties to know, especially essentially important for cycling process. However, the ab initio simulation is known to have a challenge for reliable simulation of ionic conductivity at room temperature. Here I list you two of the example. The first one is lithium-7 P3S11, and the second one is the Li3 yttrium chlorine 6. For both of the system, you can see the AMD simulated result is a few times higher or even more than 10 times overestimated than the experimental measured room temperature ionic conductivity. And the activation energy is actually underestimated. We attribute this error of those AMD results to two limitations in those previous AMD works. The first is high computational cost. If we look at the result of the LYC system, we can see the AMD results are all collected at temperature at or above 500 Kelvin, while experimentally, those relevant temperature range is actually in room temperature regime that's below 400 Kelvin. This is the same trend in the LPS system. This is because the AMD is so expensive that we're only able to simulate fast diffusion at high temperature. And then we assume the activation energy is constant. Then we extrapolate down to room temperature to get the diffusivity and ionic conductivity at room temperature. We know that this assumption of constant activation energy will fail for materials with non-Arrhenius behavior. For example, here, the lithium less than titanium oxide. So from experiment, we already know that at around 400 Kelvin, which corresponds to 100 degrees Celsius, there is a transition in the activation energy. So AMD will for sure fail. I mean, the analysis we did for AMD will for sure fail for this material. And there's another limitation in previous AMD work, which is that they're only as accurate as the DFT functional used in their simulation, which is the typical PBE functional that is known to have the error of overestimation for lattice parameters. And this leads to some error. So I want to emphasize here, those two limitations of AMD can all be traced back to the high computational cost of ab initio simulations. And it's probably possible for us to solve those challenges with machine learning interatomic potentials. So what is MLIP? Here I give you a animation of motion for water molecule at 300 Kelvin. So the motion derived from Newton's law of motion, while the force on those atoms are derived from the potential energy surface. Traditionally, there are two ways to define the potential energy surface. In classical molecular dynamics, some rigid functional forms are defined to get those potential energy surface. And this method is quite scalable. It can be applied to more than millions of atoms and more than hundreds of nanosecond or even microsecond scale simulation. However, their transferability and accuracy is known to be weak because of the relatively simple functional form. While for ab initio molecular dynamics, AMD is known to be highly transferable and accurate for the whole periodic table, while its scalability is poor in the way that it's only applicable to below nanosecond scale simulation and for at most hundreds of atoms. And in recent 15 years, the machine learning interatomic potential actually emerged as a tool that has been verified to combine the accuracy of AMD and the efficiency of classical potentials. So how does machine learning internal potential work to achieve this great performance? So when we talk about machine learning internal potentials, we are actually referring mostly to local descriptor-based MLIPs, which hold the locality assumption. So this locality assumes that the interaction for an atom with its neighboring atoms is the most crucial, while interaction for an atom with distance longer than a certain cutoff range can be neglected. And under this assumption, machine learning internal potentials define some sort of basis function. For example, here the B alpha, so that to encode the geometrical information of neighboring environment surrounding each center atom. And with this B alpha, we can use this equation to express the atomic energy. So here is some trainable coefficient, and it multiplied with the B alpha, whose summation equals to the atomic energy. And the summation of the atomic energy represents the total energy predicted by the machine learning internal potential. And with some machine learning algorithms like linear regression or artificial neural networks, we can fit those trainable parameters so that the total energy predicted by machine learning potential match with the ground truth, which are usually DFT results. Especially for the moment tensor potential, it defines this moment tensor descriptor to encode the structure information. So in this moment tensor descriptor, we have the F mu, which is the radial part. That is a summation of the product of this trainable coefficient C with the radial basis function Q. And this radial basis function is defined this way so that it's smooth and it decays to 0 at cutoff radius. And it also has this angular part, which is the outer product of V times for the vector of vector pointing from the center atom I to neighboring atom J. So later on, I mean, you can imagine that for each atom, it has a set of different moment tensor features from these descriptors. And those different features differ because they have different values of mu and V. And then a tensor contraction is performed to this different set of descriptors to get the scalable, the scalar basis functions, the alpha. So that's how MTP defined the local environment descriptor and express the total energy of a system. So according to the benchmark by Yunxin Zuo in 2020, we can see that MTP actually achieved the state-of-the-art trade-off between computational cost and accuracy compared with a few well-known machine learning internal potentials. And that's why MTP is essentially the tool that we are going to use in our simulation of solid electrolytes. And I also want to mention a very important challenge for all machine learning internal potentials, which is so-called extrapolation. Here in this schematic diagram, the black curve represents the ground truth potential energy surface, usually in DFT, and the orange curve, which is dashed, it's represent the predicted result from a machine learning internal potential. You can see that MLIPs have very good matching with the ground truth result in the training domain for prediction of structures in the training domain. However, for prediction of structures that is out of the training domain, the so-called extrapolation behavior will be attempted, and the prediction result is not guaranteed to be reliable. So that's why it's crucial for our training set to have a diverse coverage of configuration for us to have a reliable machine learning internal potential for diverse simulation scenarios. And to detect this extrapolation behavior, the moment tensor potential developers actually invented a way to quantify this extrapolation. So in their method, we firstly need to find this matrix A, which is represents the most distinct M training structures from the whole training set. This matrix A is constructed as a M times M matrix in a way that each row represents the basis function of one configuration in the training set. And there is M configurations so that this determinant of this matrix A is maximized a set of structure so that in a way that these M structures represent the most distinct structures in the training set. And by comparing any new configuration to this training set, we can know if the new structure tends to have extrapolation behavior or not by the MTP. So for any new configuration, we calculate this this extrapolation grid gamma, which defined in this way that this is the maximum value of the vector of the feature vector of that configuration times the inverse of the matrix A, so that if this value is larger than 1, it means that our new configuration is more distinct than some of the existing structures in the training set. So by this rigorous definition of extrapolation behavior, MTP is able to achieve this so-called active learning scheme. So in this workflow, this is a training data sampling workflow, and we start with some pre-trained machine learning internal potential to do molecular dynamics on some target simulation scenarios. And for every new configuration emerge in this molecular dynamic simulation, we calculate its extrapolation grid. And if the extrapolation grid is higher than some certain threshold, the MD simulation will be stopped. And that structure will be processed by DFT to get the accurate energy and force, which will be augmented into the training set. So this iteration and the model will be retrained. So this is a cycle of iterative improvement of machine learning internal potential, and it will end until no extrapolation attempt is detected on that target simulation scenario. So this is a very effective method to collect training structures. However, it can be effortful, time-consuming, especially for larger systems, because of the iterative way of augmentation. Okay. And lastly, in my introduction, I would like to also introduce the material three-body graph network, in short, M3GNet model. This is essentially a deep learning graph neural network model, and here is the framework of this model. So in the featureization step, it uses graph featureizer to process the geometry information, atom and bonds into node feature and edge features. It also performed many body computation to incorporate the bound angle information into the feature space. And in the main block, we perform many body to bound and graph convolution operations to iteratively, to sequentially update the bound features and atom features, and optionally the global state features, so that after n cycles of this n block, main block operations, the atom feature of this M3GNet model can incorporate the information of interaction with its neighboring atoms that within n times of the cutoff radius during the featureization step. And after that, these atomic features are used to predict the atomic energy, whose summation again equals to the total energy of the system, just as all the other machine learning internal potentials. Because of this deep learning framework, it actually enables the possibility of a universal machine learning internal potential model that can be trained on the whole periodic table. So indeed, this M3GNet is fitted with more than 100,000 training data points, which are DFT data from the material project that spans over 89 elements on the periodic table. And this model is verified to have very good reliability to do structure optimization. You can see that it's almost no difference with the DFT relaxation result for the simulation of materials included in the materials project. So this model enables a lot of new possibilities, like large-scale screening of hypothetical materials and efficient sampling of structures. So before going to my results, I would like to point out the major gaps and objective that I want to deal with in my PhD study. The first one is the challenging, reliable simulation of room temperature ionic conductivity of solid electrolyte. And our solution is to develop MLIPs for direct simulation of ionic diffusion at room temperature with long time and large size scale MD simulations. The second gap is the unknown origin of low or high green boundary resistance of perovskite oxide solid electrolyte. We will use this time active learning to fit machine learning internal potentials to study the local chemistry and regional diffusion at green boundaries. And third one is the effort for process of training data sampling. And in this, we develop a new method called direct sampling. to construct a robust training set actually in one shot. So let's start with the first topic that I want to discuss for my PhD study, which is bridging the gap between simulated and experimental ionic activities in lithium superionic conductors. So in this study, we use this workflow to fit moment tensor potentials for these 3 lithium super ionic conductor systems. In this workflow, we first perform DFT realization to get the ground state structure. Then we perform AMD simulation to collect 1,800 structures for each lithium superionic conductor. And we conduct DFT static calculations to get accurate energy and forces as training data for different for different systems. And MTP is fitted with those training structures and data. In this workflow, I want to highlight that we consider different choice of DFT functional, which is PBE and OPTP88. I mean, the choice of different functional choose in a way that we use these 2 different functional to perform the AMD to generate the structures. And we also use different functional to calculate the energy and forces. So the labeling for this moment tensor potential is in a way that the functional labeled in front of the comma is the functional we use to generate the structure. And the one used after the comma is the one we use to collect the accurate energy and force data. So with those training data, we fitted moment tensor potentials for these 3 systems. And here as an example, we show that for the LPS system, in the parity plot, we can see for both energy and forces, all those 3 moment tensor potentials reproduce the DFT result with very good, very low error, which is mean absolute error of below 3 MeV per atom for energy, and for force it's around 0.1 EV per angstrom. And if we look at the simulation result of firstly the geometry realization with different method, let's look at the DFT result first. So we can see that this is the comparison of DFT result with experiment. The arrow shows the result for different DFT functionals. And for LTO, we can see that these 2 functionals gives a similar result. While for LYC and LPS, we can see that the PBE significantly underestimate the density for like 3 to 5%. While for the OPTP88, it has overall better accuracy for the density of the structure. Yes. Yep. So well, for the MTP, we want to draw the conclusion that it actually reproduced the DFT error. For example, here for LTO, you can see that both the MTP has around -2% as underestimation for the density, while the same trend can be observed for LYC. And another interesting thing I want to highlight is here that actually we can see that the MTP reproduced the trend of DFT functional that is used to generate the training energy and forces. This is reflected by the fact that here, no matter which functional is used in the generation of structures, the MTP always reproduce result of the DFT functional after the comma, which is the one used to generate the training energy and forces. We observe similar trend for equation of state simulation for all those 3 systems. For LTO, the PBE and OPTP88 got a very similar result that's indistinguishable. While for LYC and LPS, we can see clearly there a significant difference, and MTP reproduce again the DFT result with the functional that's used to generate energy and forces. It's a good thing that our potential, because our training data is DFT, so we need to reproduce the DFT results. So MLIPs are trained to reproduce the DFT results. So yes. Yeah, so if we look at the training error or test error, it's actually very low because it reproduces all the simulation result by DFT. Yeah. Yeah. Okay, let's go to the simulation of room temperature ionic connectivities. So we use those different set of moment tensor potentials to simulate room temperature ionic connectivity. You can see that in this simulation, we not just simulate the high temperature region above 500 Kelvin. Also, we study the room temperature region that's below 500 Kelvin, okay, directly even at 300 Kelvin. And we can look at the result in this table. So firstly, for LLTO, so both the moment tensor potentials can get very good matching with the experimental result at room temperature. And they both capture the non-Arrhenius behavior, as you can see from the transition in activation energy at around 500 Kelvin. Well, for the LYC and LPS system, we can see that the MTP trained with the PBE functional actually has severely overestimated room temperature ionic connectivity, while the MTP trained with OPTBA functional gives reasonable matching with experimental result. And they also capture the non-Arrhenius behavior. We further studied the system by analyzing the diffusion trajectory. And you can, and in this plot, I give you the diffusion trajectory at two different temperatures, 500 Kelvin and 300 Kelvin for all those three systems. This is above and below the transition we observe in the Arrhenius plot. And we can see a clear trend. The decrease of the activation energy at high temperature is coupled with the activation of new diffusion pathways. So here I want to draw a quick conclusion for this study, where we show that MLIP reproduce the DFT simulation by functionals used in the generation of training energy and forces instead of the functional used for training structures. And also MLIPs trained with the more accurate functional, which is optimated here, is able to get room temperature ionic connectivity with good accuracy by capturing the non-Arrhenius behavior coupled with the thermally activated diffusion pathways. And seeing this very good new result, we are excited to apply this method to other systems that is practical for solid electrolyte. For example, the complex green boundary structure. And that's why we start this project, which is a collaboration with Tom Lee in Xiaoqing Pan's group at UC Irvine, and also Shu Ting Ko from Professor Jianluo's group at UCSD. So this work, we name it as fast ion diffusion at green boundaries of the oxide perovskite solid electrolytes, LSTZ 0.75 and LSTNZS. The reason why we want to study this is that we know the LLTO is a superionic conductor. However, its practical application is actually blocked by its very large green boundary resistance. Well, for the LSTZ family of material, it has exactly the same perovskite structure as LTO. Well, interestingly, for this material, the green boundary resistance is actually low, so that the overall ionic activity is higher than LTO, making it a more promising material as solid electrolyte. So for LTO, there has been extensive experimental result and simulation result to explain the low green boundary resistance. From experiments, we know that there are formation of titanium oxide and also lithium depletion at green boundary region. Well, from computational result, we also see that for different low sigma green boundaries, the diffusivity values are at least one order of magnitude or a few orders of magnitude lower compared to the ionic activity in bulk. And activation energy is also higher in the green boundary region.
This competition is it AME or
it's classical potential? Yeah.
classical?
Yeah. So that's the only thing we can find. Yeah. According to the computational result, you can see the
But
Okay. Yeah, I agree. I mean, the classical potentials less accurate, especially they don't have very good verification for those large scale simulation at complex structures like green boundary. So again, we want to fit a machine learning internal potential to study this system. And this is the initial workflow we used, which is similar to the previous work. And here we use the PBE functional because we see that the DFT result with PBE functional has actually already very good matching with experimental result in terms of lattice parameters. However, when we apply this moment tensor potential to simulate some practical scenarios, which is green boundary models, we can see that there's some unphysical behavior. Here is the shrinkage of volume in the energy minimization. And on the right is the equation of state, where it's definitely unphysically low at a shrinked volume. So it tells us that we need to augment the training set to have broader coverage. So how do we do this? It's definitely very expensive and more or less unaffordable to do AMD again for this large green boundary structures that's usually over hundreds of atoms. So this time we use the active learning workflow that we discussed in the introduction to sample the diverse structures. And you can see that with iterations of active learning, we can get improved simulation reliability. And also our prediction for green boundary energy also converged to DFT result after the active learning iterations. And an actual site of verification is done for the green boundary energy simulation that is out of the training set. So for those green boundary orientations, we got reasonable error below 0.15 joule per meter square for those green boundaries we simulated. They're okay, yeah. Yeah, well, those MCMD and MD simulations are performed at elevated temperature. Yeah. Okay. So let me continue. And so I want to show here, like with MTP, we can effectively collect some green boundary structures. And we are now confident to apply this to some larger scale simulations. So the first scenario we apply to is to study the A-site lithium-strontium ordering in the bulk structure of LSTZ 0.75. So in this case, at 0 Kelvin, the lowest energy structure actually has the alternate stacking of lithium and strontium on the A set. So this has the lowest energy, and this corresponds to the ordering parameter, which is equal to 0.778. Well, when we perform MCMD simulation to allow the atom swap between A site, lithium and strontium, we can see that at elevated temperature above 723 Kelvin, we can see the order parameter actually decreased to 0 during the simulation, which means that you can see here the A set is no longer ordered, and the lithium strontium are fully disorderly distributed in the A set. And we also we use molecular dynamic simulation to study the diffusion for different models obtained from MCMD simulation at different temperature. And we see that the structure model that has the more disordered A set actually give higher ionic conductivity. So this trend has been reported for the lithium lanthanum titanium oxide case, where higher calcination temperature can promote the A set disordering and thus increase a few times of room temperature ionic conductivity for bulk system. And this is a good verification for our model. We then apply the model to study the green boundary composition and lithium diffusion. In our study, we have 5 green boundary models. 4 of them are low sigma green boundary models, and the other one has a relatively large sigma of 51 to mimic general green boundary. And we again applied hybrid Monte Carlo molecular dynamic simulation at the experimental calcination temperature of 1573 Kelvin to observe the evolution of green boundary cation composition. And you can see that for all those 5 systems, we don't see any lithium depletion at green boundary, Well, actually, at the lower three cases, there is some increase in the lithium concentration at the grain boundary, which is accompanied with some formation of strontium vacancy at the grain boundary. And by checking out the swapping energy by DFT, we see that actually by looking at the first line of lithium and strontium swap from grain boundary region to bulk region, we can see that the lithium is more energetically favorable than strontium to stay at the grain boundary for this material. And we also studied the Arrhenius plot with on-time MD simulation. And this time we see that for our system, by the analysis of lithium diffusion at grain boundary region, we see the diffusivity is only 2 to 3 times lower than the diffusivity in bulk, and the activation energy in grain boundary and in bulk are actually comparable. Another important information is that the diffusivity along the grain boundary and across grain boundary are also comparable. So that's how we study the grain boundary of LSTZ material. And we also continue to study this system by looking at the compositionally complex perovskite oxide. For this work, our collaborator, again, shooting call from Dr. Jianluo's group at UCSD, discovered this new family of single-phase compositionally complex perovskite oxide that can have 4 elements on the B set of this oxide perovskite. Those can be tantalum, niobium, zirconium, hafnium, or tin. And this composition of LSTNZS has the highest room temperature ionic conductivity of 0.218 millisiemens per centimeter. So that's why we're going to study this system. And we applied the same workflow of active learning to construct MTP for this LSTNZS system. Well, this time I want to highlight a little bit that we did spend a lot of effort to get this MTP converged, which took us more than 200 active learning iterations. But once the simulation is converged, it tells us that our MTP is reliable to simulate up to more than the experimental calcination temperature. And also we got very good matching with the DFT grain boundary energy. And similarly, we applied this moment tensor potential to study the grain boundary composition and diffusivity. In this system, we also actually got comparable results for the LSTNZS with the result in LSTZ 0.75. And to give a conclusion of this study, for these 2 materials, for the LSTNZS, LSTZ 0.75, we found that the disorder lithium strontium on A side actually promotes the bulk ionic conductivity, and lithium depletion at grain boundary, which known as the major cause for high grain boundary resistance for LTO, we didn't observe it in the LSTZ system. And the fast lithium ion diffusion is promoted with the strontium vacancy at both the low index and high index grain boundaries, which overall together contribute to the low grain boundary resistance of this LSTZ family of material. And especially for this LSTNZS system, I want to highlight again, active learning of MTP requires significantly more iterations until we reach convergence. Okay, so here comes the last study of my PhD work, which is robust training of machine learning interim potentials with dimensionality reduction and stratified sampling. To begin with, I want to mention some extrapolation tests of M3GNet. Firstly, I want to show you some interpolation test. So this is M3GNet performance on all the 7,270 sodium-containing materials in the material project. You can see that more than 75 of the result actually has a very low error of below or equal to 0.37 EV per atom for relaxation energy. So those structures are considered as inside the training domain of M3GNet because they are contained in the materials project. However, we really want to test and challenge the limit of the M3GNet model by some extrapolation. that's on the hypothetical materials not included in the training domain. This time we take the hypothetical materials randomly selected in the matterwords.ai database. And we find that actually this error increase for at least 5 times for those extrapolation. So that's why we say M3GNet is also less accurate for those hypothetical materials that is not in the training data. And to try to improve the accuracy of M3GNet, what we can do is naturally we can try to expand the space covered by the training set. Let's first look at the existing training set of M3GNet, which is built by a manual sampling method, which select the first, middle, and last realization snapshots from the 62,000 materials in the materials project realization trajectory. And this attempt was to sample a diverse structure space. But if we look at the PCA space of M3GNet feature, we can see that although these green dots cover the majority of the feature space, there are definitely some regions that's on the boundary of the feature space that's not sampled. And more importantly, if we look at the energy, force, and stress, which are the properties that we'll be using in the training process of M3GNet, we see that in some relatively uncommon value regions, like the larger energy and large force regions, those data in the material project are not sampled by the M3GNet. By this, I mean by this manual sampling scheme. And this tells us there is still some space for improvement if we can find a way to cover all those diverse structures in the materials project trajectory dataset. And that's how, we invented this dimensionality-reduced encoded clusters with STRATIFIED sampling method. In this sampling method, so given a configuration space, for example, here, the material project dataset, we can use M3GNet model to do the featureization to process the structures into features. And then we do a dimensionality reduction with PCA to get the reduced feature space. And the next crucial step is that we do a clustering for those structures according to their location in the feature space. In this way, we can actually cluster common structures into clusters and some very uncommon structures into those uncommon clusters. And following this step is the stratified sampling, where we treat those different clusters equally and sample a same number of structures from different clusters. So this way, you can imagine that we will select not only the common structures from the space, but also the very uncommon structures. And that's how we construct a hypothetically more robust or larger or more distinct data set from this existing configuration space. And by looking at the coverage of this direct sampling and compare with the manual sampling, we can see firstly in the feature space, the previously uncovered boundaries of feature space is covered. And I want to mention that this direct sample dataset has almost exactly the same size, which is around 15%. The same size as the manual sampling dataset, which is around 15% of the total dataset. And also looking at the potential energy surface property coverage, we can see that the orange bars almost overlap with all those purple bars representing the total dataset for those relative uncommon potential energy surface properties. So this slide tells us that direct sampling indeed gives a better coverage for those more diverse structures from the configuration space. And then we use this direct dataset to train M3GNet models and compare the result with the manual sample dataset. So the above are the parity plot for energy, force, and stress calculations by the M3GNet trained with direct dataset, and below is by the manual sample dataset. We can see, for example, for force, the M3GNet direct has a test error around 0.1 EV per angstrom for both the test set, while for the manual sample dataset, it has a much larger error for the direct test set, while much lower error for the manual sample test set. This tells us that the M3GNet training with direct set gives a more consistent accuracy over the two test sets, especially for those more challenging cases. And we apply this M3GNet direct to the question that we previously discussed, which is extrapolation on those unseen structures in the hypothetical material database. And we can see that for example, for the sodium-containing case, we have improved performance. And this is the same case for the sulfur-containing compounds. While for oxygen-containing compounds, we have comparable results with the manual sampled data set, M3GNet training with manual sampled data set. And to continue discussion, I want to show you this plot that I showed before, where we can see that there's some very large error of test for M3GNet, which correspond to more than a few EV per atom error for energy. And this is definitely very large. So that's why we redo the DFT calculation with a static calculation to get the accurate energy and force information to see if this is really error of our model or actually some noise in the training data. And what we found is that in this plot, we see there is a large correlation between the noise in the test energy, which is the error of the DFT relaxation energy and force with the static DFT energy and force. Energy here, and on the y-axis is the M3GNet test error. So there is a large correlation between the M3GNet test error with the noise in the training in the test set. Okay, this tells us that if we improve the training data and test data with reduction of noise, then we will likely result in M3GNet with improved accuracy. So we indeed perform some static calculations for the large force structures with large forces. And we, again, confirm there is a noise in this energy in the materials project data. And by replacing those large force structures data with our newly calculated data, we find that the M3GNet, both the manual sample data set and direct sample data set, can result in an M3GNet that has improved simulation reliability. In this case, we performed molecular dynamic simulation at 3000 Kelvin for titanium hydrogen. And you can see that the original M3GNet with the version 0.1 is not able to get a reasonable convergence of the simulation with even very small step interval of 0.1 femtosecond, while our M3GNet manual sampling or direct sampling model can reliably complete the simulation with a reasonable time interval of 0.5 femtosecond. So this highlights that it's very crucial to reduce noise in the training set. And that's how we get a more reliable M3GNet direct data model with our method. So the second part of this study, I want to firstly recall the result I showed previously, which is the active learning iteration that we used to fit the model for the LS10ZS material. And here we took more than 100 active learning iterations to get the simulation converged. And especially you can see that most of the active learning iterations are actually performed in very small amount of MD steps. That's within 1% of the 100 picosecond. And if we look at some results from the MTP developers, you can see that for learning on the fly, which is active learning from scratch or from a selected initial training set, there can be significant difference in the computational cost, which tells us that it's very crucial to get a good initial training set to get fast active learning convergence. Well, the optimal scenario we can imagine is to sample a robust training structure set actually in one shot. And we try to achieve this goal with the direct sampling coupled with M3GNet molecular dynamics. In this case, we generate this structure set with M3GNet molecular dynamics, for the titanium hydrogen system. So there are in total 274 simulation scenarios of molecular dynamics containing different lattice systems and different temperature range, and also different system type. And we performed the MTP active learning on exactly the same 274 MD scenarios to collect the active learning training set. And the third set is an AMD set that is done on some selected temperatures. So in this PCA feature space, we can visualize the feature space covered by these three different data sets. And what we see is that M3GNet MD structure can mostly cover the features sampled by MTP active learning and by AMD structures. And we use direct sampling to sample structures from the M3GNet MD trajectory. We can see that compared with manual sampling, direct sampling can better cover, again, those relative rare region of the feature space, which is the same case for these plots. And we fit the MTP with two data sets. The one training set is the direct training set, and the other is the active learning training set. And we find that by looking at this parity plot, those two models all give very good matching with DFT result. While especially for forces, those two models give almost the same results in terms of the MAE for test. Well, for the energy, the MTP direct has 1 ME per atom larger error compared with the one sampled with active learning, but it's still more or less, it's quite reasonable. And then we perform large-scale MD simulation to study the hydrogen diffusion in this titanium system. And what we found is, like in the first plot, we see that these two MTP matches very, very well with each other for the trend that hydrogen diffusion is faster. The fastest in the BCC system, while it is the slowest in the HCP system. And on the second plot, we show that these two MTP models all get reasonable matching with AMD result at 1000 Kelvin. And another interesting test we did is to see if our method can really achieve our initial goal, which is to try to skip or decrease the active learning iterations we need in the structure sampling process. So in this case, I show you two scenarios of active learning training. The case one is starting from scratch, which contains 91 initial structures of MD. And the second case is starting from the direct sampling dataset. You can see that if we start from direct sampling dataset at temperature of 300 and 1000 Kelvin, all the 91 MD simulations are already reliable without any active learning iteration. So this tells us that our direct sampling can serve as a very good sampling method to just in one shot sample the structures as training data for MTP without further active learning. While for higher temperature, in this case 3000 Kelvin, we still need 5 iterations of active learning to get all the simulation reliable. But this is a few times smaller in terms of active learning iterations compared to the active learning from scratch. Yeah, so that's why I say compare with starting from scratch, starting active learning from the direct set promotes the convergence of active learning by providing a robust training set. And to draw a conclusion for this third study, direct sampling outperforms manual sampling with domain expertise to distill those representative structures from the material project database, and thus results in a reliable M3GNet that has improved simulation reliability. And secondly, combined with the M3GNet molecular dynamics, direct sampling can efficiently generate diverse training set for specific material systems and decrease or even eliminate the need of active learning iterations for MLIP training. Okay, so I will go to the summary slide to summarize what I've done in my PhD for the defense. So firstly, we investigate the method, use MLIP to do accurate simulation of ionic conductivities at room temperature. And in the second project, we use active learning to feed MLIPs to study the regional composition and fast lithium ion diffusion at grain boundary of solid electrolytes. And in the third study, we come up with this direct sampling method to do robust MLIP training, to generate robust MLIP training set in one shot. And as an outlook obtained or inspired from these studies, firstly, I would say MLIPs can enable more reliable screening of solid electrolyte materials from very large candidate pool. And secondly, in terms of simulation reliability of MLIP, especially for complex scenarios that usually requires large size to simulate, that's beyond the scale of DFT. Those simulations requires more rigorous uncertainty measurements for us to verify our results from the MLIP. And thirdly, the feature space of M3GNet encodes very comprehensive information correlating the structure and properties, and it opens a lot of new opportunities for material simulation. And here I want to list my publications during the 4.5-year study here, and highlighted 4 publications are mentioned in the defense today. And I also got a chance to give quite a few presentations and posters in different conferences. And lastly, in the acknowledgement section, I want to express my gratitude to my advisor, Professor Shui Ping for his guidance and support for me to complete this 4.5-year study. He gave me adequate amount of pressure and encouragement during the process, and I really hope that I can continue to learn from him, but I need to jump out of the comfortable zone, so it's time for graduation. And also to thank my dissertation committee, Professor Benju, Professor Zheng Chen, Professor Jian Luo, for their support since my Senate exam. And also, I want to say special thanks to 3 members of the Materials Virtual Lab, who are Dr. Yunxin Zuo, Dr. Shi Chen, and Dr. Zivi Kuo. So the first 2, Yunxin and Shi, they were my first teachers in Materials Virtual Lab, and they helped me to start my study. And I can imagine those works will take a few times longer time without their help. And they are also great examples for me as a PhD researcher, also a good person. And Dr. Zivi Kuo, who joined the lab just around 1.5 years ago, but discussion with him has benefited me a lot for better understanding of the methodology of machine learning term potentials. And I hope I can have the chance to continue to collaborate with them. And I also want to say thank you to collaborators in the Materials Virtual Lab, including Dr. Manas, Savastika, Joying, Madi, Zihan, Renze, Adesh, Vibu, David, and all the other members in the Materials Virtual Lab who supported me not only scientifically, but also in daily life. Also, I want to say thank you to my experimental collaborators, Professor Jian Luo, Professor Xiaoqing Pan, Professor Shirley Meng, Professor Raphael Clement, Tom Lee, Shooting Call, Dr. Elias Sapti, Philip Redley, and Sam, and all the other experimental collaborators, without whose support, those works impossible. And also, I want to express my gratitude to my mentors during 2 summer internships in Lawrence Livermore National Lab and in Robert Bosch, Dr. Tuan An Pham, and Dr. Nicholas Molinari and Dr. Karim Gadarab, for their support and the freedom they gave me during those internships. And lastly, as acknowledgement plus, I want to say thank you to my wife, So no matter what happens at school or at work, I mean, I always know there's someone supporting me at home. So I'm very happy to have her. And I want to say thank you to my family. This is the departure photo taken in the airport. My grandfather already passed away, so he cannot witness. But it's still, I think, yeah, I want to say thank you to them. And also my friends. Sorry. Yeah. So this is the first year MATS last year, and I hope that they can graduate.
Rubbing it in their faces. All right. That was a very nice presentation, and I want to open it up for everyone to grill tea, of course. Especially the MATS who has not graduated. It's time to take your revenge, right? Any questions?